You learned previously that an inherent property of an object is its mass. An object with a smaller mass has a smaller inertia compared to an object with a larger mass. Along with mass, another inherent property of an object is its electrical charge. The concept of electrical charge has been around for centuries and has its roots in a simple experiment first reported by Thales of Miletus in 600 BC. If you rub a plastic rod with fur and suspend it by a string, and then rub a second plastic rod and bring it near the suspended rod will move away. However, when a rod of glass rubbed with silk is moved close to the suspended plastic rod will move toward the glass. The conclusion that was made from this experiment is that two different types of electrical charges exist, and that opposite charges attract one another, and like charges repel one another. Benjamin Franklin named the two different types of charges positive and negative. The basic unit of charge in the MKS system is the Coulomb, which is abbreviated by capital C. On an atomic level, individual particles carry charge. Protons are positively charged and electrons are negatively charged. A third type of particle exists called the neutron. Neutrons have no charge. Protons and electrons carry the same amount of charge, denoted by the letter Q. This basic unit of charge has been determined to be 1.60 times 10 to the minus 19 coulombs. The neutron, which is neutral, has no charge. Even though protons and electrons carry an equal but opposite amount of charge, their masses are very different. The proton mass is 1.67 times 10 to the minus 27 kilograms, while the electron mass is 9.11 times 10 to the minus 31 kilograms. The neutron's mass is almost the same as the proton's mass. These are very small numbers, but the thing to keep in mind is that protons are almost 2,000 times heavier than electrons. Atoms are made up of a nucleus of positively charged protons surrounded by negatively charged electrons. On average, most bulk objects have an equal number of positive and negative charges and are thus charge neutral. Thus, when all of the charges in an object are added together, their sum is zero. In our simple experiment in which the silk and glass were rubbed together, a small amount of charge was transferred from one object to the other. In this case, the rod ended up with a net positive charge. It can be shown that the silk used to rub the glass ended up with a net negative charge. Thus, rubbing the silk and the glass rod has rearranged the charges, but it is important to note that no charges were created or destroyed in this process. A general theory of charge is that total charge is always conserved. This is analogous to the statement of energy conservation. This hypothesis has withstood close experimental scrutiny, and no exceptions have ever been found. In terms of the behavior of their electrical charges, materials usually fall into two classes: conductors and insulators. In conductors, negative electrical charges flow freely. Conductors include the human body and metals, such as copper wire. In insulators, charges do not flow easily and can build up on its surface. Insulators include glass and plastics. From a practical point of view, the reason it is unwise to touch a current-carrying wire with your bare hand is that both you and the wire are conductors. Thus, if you touch a wire, charge can flow freely through your body. If instead you use an insulator, such as a plastic glove, to cover your hand before touching the wire, you do not get shocked. since charge cannot flow through the plastic to your body. Charles Coulomb carried out a series of experiments in the 1700s to measure electrical attractions. From these experiments, he deduced the law that governs electrical attractions. Let's say we have two positive charges, Q1 and Q2, separated by a distance r. It can be shown that the electrical force of one charge on the other is proportional to the product of the two charges and inversely proportional to the square of the distance between them. The proportionality constant has been determined to be equal to 1 over 4 pi epsilon 0. The factor epsilon 0 is known as the permittivity constant and has a value of 8.85 times 10 to the minus 12 coulombs squared per Newton meter squared. This expression for the electrical force is known as Coulombs Law, and, like any force in the MKS system, it has units of newtons. Like all forces, it is a vector, and it points in the radial direction either towards or away from a spherical charge. For two positive charges, the force of one charge on the other is in the direction away from the charge. Thus, if released, the two charges move away from each other. This shows that like charges repel one another, as was discussed previously. If one charge is positive and the other is negative, the force on the negative charge is towards the positive charge, as indicated by the negative sign in Coulomb's law. In this case, the force causes the charges to move towards each other, supporting the statement that opposite charges attract. If more than two charges are present, the total force acting on one of the particles is simply the sum of the forces exerted on that particle by the other particles. For the example here, the force on charge 1 is equal to the force of charge 2 acting on charge 1 plus the force of charge 3 acting on charge 1 plus the force of charge 4 acting on charge 1. Note that the total force acting on charge 1 is the vector sum of all the individual forces. Let's calculate the force acting on a charge that is situated between two other charges. The charges are positioned along a straight line and are separated by 1 meter and 2 meters respectively. The outer two charges are positive and the center charge is negative, with the amount of charge on each as shown. What is the force acting on the charge in the center? We'll call the central charge charge number 2. What is the total force acting on charge 2? Correct. What geometrical simplification of this problem can be made for the force? Correct. Since the charges are along a straight line, the problem reduces to one dimension. Assuming charge 1 is at the origin, what is the force of charge 1 acting on charge 2? Correct. What is the force of charge 3 acting on charge 2? Incorrect. Check the signs of the charges. Correct. Using the given parameter values, what is the total force acting on the charge in the center? Correct. What is the significance of the negative sign in the answer for the force? Correct.